Okay, so hello and welcome with our next video session. So we have here a analysis of a frame wherein it's getting complex. So complex in a way that there is now a diagonal member here. So it is getting interesting if we have a diagonal member, and with the diagonal member there is also distributed load on that diagonal member. So let us remember that there will be two types of distributed load on diagonal members or in any member, of course. So these are distributed loads along the global Y and along the local Y. So what is the meaning of this? So when we say along global Y, it is a vertical downwards. Okay, it's always the y-axis. So the y-axis that is not rotated. So the normal y-axis we have. So if we have an inclined member here, okay, it could be this type of loading. So if you notice, the distributed load is globally located on y, the regular y we have. Or it could be like this one. So this is the inclined member wherein the loading is along that inclined member. However, the orientation is along global y. So the usual y. So y is always vertical here. So you might probably ask what's the difference between these two. The difference is that the divisor of this is along this horizontal distance, say L, and for this one it is along the length, so that the length coverage of this loading is this one. So there is a difference in the length here, that if you're going to resolve that into the inclined member, if you're going to resolve this distributed load, you have a different divisor here. Of course, there will be longer divisor if the distributed load is like this. Okay? It is along the diagonal. Unlike here, it is along the horizontal line. Okay, so but they are similar in the sense that the pressure is within the global y-axis. Okay, for the local y distributed load, the pressure is always perpendicular to the inclined member, and your x and y is rotated along the axis of the member. So when the axis is along the member, the inclined member, that is what we call along local y axis. So now, what is the difference between global y and local y? Well, in terms of its force, of course, the mother force for local y is like this. So it is perpendicular to the member, having the components. So if this is P, we have Px and Py as its component. So this is the mother force for this local y distributed load. How about for global y distributed load? So you can clearly see now the difference between these two, because this time your mother force is vertical. Okay, so no matter what is the inclination of this member, your force is always vertical. And just the same, we will be having a component of Px and Py whenever you resolve it along the inclined plane, or you resolve it along x and y axis. So basically, the principle in dealing with this inclined member, remember that we always resolve the forces along the parallel and perpendicular axis to the member. So say if we have here an inclined member, say exposed to some vertical forces here, say that is P1, P2, we will find a way to resolve all of these forces parallel, and perpendicular to the member. So parallel and perpendicular to the member. So therefore, P1 will be having Px and Py. So interchange that one. Of course, we would want to enter the subscript here, P1x and P1y. And for P, we have Py and Px. And P2 has P2y and P2x. So if you notice, all of the components are parallel and perpendicular to the member. So if this is the member, you just get the parallel axis and the perpendicular axis. So that will be now your rotated axis x and y, and try to resolve all of the forces parallel and perpendicular to this axis. And that is the key to the solution in a shear and moment diagram of frames having a diagonal member. So let us now consider this example. So this, we have a column and an inclined beam here. So this is 10 by 10. So it is obvious that this has a 45 degrees angle because we have equal leg here. And then the first step is to draw the FBD of this free body diagram. And then we're going to establish the load diagram. And then the shear diagram. Then the moment diagram. Okay, so illustrating the FBD. So we'll just have to utilize this beam frame here. Okay, we're going to draw. So this is the distributed load, and obviously the distributed load is global y. It's along the global y. So it is not perpendicular to the inclined members. It is all going downwards. The pressure is all going downwards. Okay, so aside from this loading, of course, we have here the pin connection. So of course there will be two reactions there, and with the roller at this point. So the first step is this one, and then we establish the load diagram. Of course, we need to complete our reaction here. So doing that, we need to resolve first this distributed load into its mother force. So this mother force is, of course, we need to refer to this. I think we need to place a value here. Say we have 0.414 pounds per foot loading. So next, we resolve this one. So we have 0.414. Of course, we need to get that distance, and that distance is square root of 10 squared plus 10 squared. Okay, so this is by Pythagorean theorem. We have 14.14 feet. So we're going to place it here. Okay, so this is multiplied by this L. So we have there 5.85 pounds. Okay, so we take moments in order to determine our reaction here. Say we have summation moments at A is equal to 0. We have clockwise 5.85 times half of 10, that is 5. Minus 10 RC is equal to 0. So is this really 10? So let us, it's best to always reflect our distance here. Say we have here 5 and 5, and we have here 10 and 10. So therefore this should be 20. Solving for RC, we have 1.46 pounds for our RC. So by summation forces horizontal. Okay, so we can say it's obvious that RAX will be just equal to RC, which is 1.46. And by summation forces Y, we can just conclude that RAY is simply equal to this vertical force here, is equal to 5.85. So we have obtained the three reactions. So next is the load diagram. So we need to draw now the load diagram here. Okay, so let us consider this vertical member here that is actually AB. So let us label what is in AB. We have going upwards 5.85 and then the rightwards 1.46, and then as we can see there will be no other external forces other than these two reactions here. Okay, so next is to determine the internal forces here in the M on the joint B. Of course, one thing to consider is to assume direction. First, for the vertical, we have vertical 5.85. Okay, you can always assume and then employ summation forces vertical, but this time it is obvious that we have a going upwards 5.85, so therefore your vertical force here should be going downwards 5.85, and this as well is leftwards 1.46. And then for the moment at B, we place it here. Say I assumed a counterclockwise moment at B. So what we do is just to take moments at B. So summation moments at B is equal to 0. We have negative MB minus 1.46 times 10. So this is 10 actually, 10 feet. So there is no other force here, so we can close it to 0. So here we notice a negative result which is negative 1.43 pounds. So again, this simply implied that we have a wrong assumption on the direction, but we'll just maintain the figure but always carry the sign of the magnitude of MB. Now, proceeding with the next member, say for the beam, we have here the inclined beam. Okay, we reflect all the opposite direction, opposite orientation of this into this. So first, we have the moment that is counterclockwise, so therefore this will be clockwise MB, and this is gonna be an upwards 5.85. Okay, and this is a leftwards 1.46. How about the distributed load here? So a while ago we have resolved that into mother force that is equivalent to 5.85 going downwards, and here it is. So getting the component, remember that this is in pounds force now. Let us get the component parallel and perpendicular to the member. Actually, we have these two component of this 5.85. Of course, we need an angle here, so that if this is theta, and that is also theta. Okay, so inclined angle and then perpendicular and vertical, that is also the angle. So why do we need to do this? Because this is our reference in getting your components of 5.85. So it is just a matter of determining what is the adjacent side and what is the opposite side. So it is obvious that the adjacent side here is this one. So if we have an adjacent side, then our multiplier is cosine. And I think your angle is 45 degrees. So about this component is actually can be projected on this. Isn't it that they are just parallel? Okay. If you wanted to transfer this force to include it on the right triangle where it involves theta here, so no problem. So just transfer that to that. This is a parallel member, and then we can clearly see that this is opposite your angle theta, and that is basically 5.85 sine of 45 degrees. So anyway, if we have a 45 degrees angle, the value of sine and cosine is are just equal. Okay, so we have an equal value for this. We have 4.14, and that is also equal to 4.14. 14. So we have just resolved these components. Okay. So further, we are going to simplify our force diagram on this section, wherein we're going to rotate, as I have said, the most essential part of dealing with a inclined member is that you resolve all of the forces into the parallel and perpendicular axis to the inclined member. So we draw the inclined member again. Here it is. And then from these components of 5.85, remember that 5.85 is a distributed load. So out of this component, we are going to distribute it again into the member. So of course, we will be concerned with this distance now. Your hypotenuse distance is 14.14. Why? Because this will be our divisor for 4.14 in order to solve for the local y distributed load. Okay, so notice that from global y, it has become local y now because it is now perpendicular to the member. So what is the value of this? Of course, we will refer to this value. Okay, 4.14 divided by 14.14. We have 0.293 pounds per foot. Okay, so that's for the component of this rotated y-axis. So again, this is the rotated y-axis and that is the rotated x-axis. How about the component of 5.85 along the component of the rotated x-axis? Say this one, 4.14. So 4.14 is a tangential force, okay? It is parallel to the member. So we distribute the tangential force all over this length again by dividing 4.14 all over your distance, okay? So we will be having here a distributed along or parallel to the member. So that is also equal to 0.293 pounds per feet. So it so happened that they have equal values. So therefore, this should also follow that is equal. Okay, and then that is placed there. So we're now done with having this global y distributed load converted as global or local y and local x distributed loads on the beam. So that is the principle wherein we take the rotated axis and resolve all of the distributed loads as well as the pointed loads on that axis. So next, we consider 1.46 on its perpendicular and vertical axis to this inclined member. Say that is your 1.46. Of course, we will be having now perpendicular and parallel component of this 1.46. Okay, so if we are going to use angle, of course, to be able to get these components here, we need to have a reference angle. So where shall we get the angle? Every time we have to refer it to the inclined member. So we'll just have to draw a horizontal line and the theta here. So this is the slope, horizontal line, this is theta. This is the slope, this is the horizontal line. So therefore this is also theta. So therefore, this component here is 1.46 times cosine of 45 degrees. And it follows that if you're going to transfer this to the other side of the triangle, you will notice that this is just opposite the angle theta. So therefore, that should be equal to 1.46 sine 45 degrees. Again, it so happened that we have a 45 degree angle. Therefore, these two legs here must be equal. We have here 1.032 and 1.032 like that. That is for the horizontal. So we're done with this. Okay, so our next task is this 5.85. Okay, so I'll just place there 5.85, and this 5.85 will have this parallel component and the perpendicular component here. So we need to have the angle here. Remember that this is perpendicular up to that inclined surface or member, and combining it with the vertical line, therefore that is our 45 degrees. Okay, so notice that this component along the local y-axis is adjacent to the angle 45 degrees, so we can say that that is equal to 5.85 cosine of 45 degrees, and automatic that this is 5.85 sine of 45 degrees. So if you wanted to transfer this to this, of course this is the vector of this force here, and notice that this is really opposite your reference angle, so that is why we are using sine 45 degrees here. So again, we have an equal value here. We have 4.14 here, another 4.14 at that point. So finally, we are done with that joint. We proceed to this joint here. Actually, we have a horizontal force here. Say that is our reaction. It was obtained a while ago. I think RC is equivalent to 1.46. Okay, so we're going to place here 1.46. Okay, so this 1.46 is to be computed in its components along perpendicular and parallel to this inclined member. First, we have the perpendicular component here. We can say that this is inclined with the vertical line at 45 degrees following the ruling on angles. Okay, so notice that your angle here is adjacent to your component. So therefore this is 1.46 cosine of 45, and that is also 1.46 sine of 45. Again, we have an equal value here, 1.032 and 1.032 there. Okay, so if you notice there are a lot of forces here, you can clean it up. Of course, starting with your column here. So I'll just pick this one. So here is your column a while ago. We obtained this load diagram, and then we just clean it. We just clean this inclined beam here. Okay, in terms of the resolved components along the perpendicular and parallel to the inclined member. So let us redraw that. We have the inclined member. Of course, we have here this one 1.032, and then our 4.14 here. We have here 1.032, this one, and then this one 4.14. So have we placed all of the values? So let us check. We have here 4.14, 1.032, another 1.032, and this one is 4.14. So actually we have two mother forces, so we yield at 4 components of this. Okay, so let us maintain these distributed loads. Okay, so both distributed loads along the parallel and the perpendicular, we have 0.293 pounds per feet. And then lastly, for this one, we have to place here 1.032 and another 1.032 there. Okay, so let us check our summation forces X along the rotated axis and the summation forces y along the rotated axis. Remember, your rotated axis is this one, x prime and y prime. So if we look at the x prime, okay, so what are those forces along the x prime? First, we have a positive rightwards 4.14, okay, less this one 1.032, less this distributed load here, so it shall be multiplied by 14.14, okay, and then minus 1.032. So this is equal to 0. Is it really equal to 0? Okay, we place there the question mark. So I think we need to check this one. Okay, 4.14, 1.032 leftwards, 1.032 upwards, and then another 4.14. Okay, so I think we have misdirected this. Okay, notice that we have a rightward force here, 1.46 sine of 45. So this should be towards right. Okay, so we'll just have to replace the sign here. This becomes positive, and then we then recompute. So now it's really equal to 0. Okay, so that's it. And then how about for y, which is rotated? So y prime is rotated axis. We have 4.14 going up. So here it is. And then the going downward force here, 0.293 times 14.14. And then of course we wanted to add this one, 1.032, and another upward 1.032. And if we equate it to 0, it will not yield to 0. So again, there will be misdirected forces here. So let us start with the transfer of the loading. So that is how to check or troubleshoot it. So first, we have 1.46 here. Originally, that is going towards left. So therefore, your 1.46 here should be going towards right. So perhaps that is our misdirection here. So just change this one onto this direction. So what happened next is, of course, it will affect this orientation of your direction. So you just have to orient this downward, and that will be rightward. So correcting that one, so your 1.46. Okay, so we have the same rightward force, 1.032 there, and then this shall be going downwards. Okay, so let us now again check our summation forces x prime. So rightwards 4.14, rightwards 1.032, leftwards this one 0.293 times the distance 14.14, and then minus 1.032, so it's really equal to 0. And then for this one, we have upwards 4.14 less this one 0.293 times the distance 14.14 plus. So I think this should be minus for this one, so because it's going downward, so that is changed to negative, and then this maintains to be positive for this reaction. So if we are going to compute that now, we have already yielded to 0 is equal to 0. Okay, so this is actually the analysis is all about. Okay, so it is just a matter of performing it, and then you self-check it by this mechanism. Okay, you must bear in mind that you always satisfy forces vertical and horizontal whenever whatever your axis is, whether it is rotated or the normal axis. What is important, you know how to check, or you have a mechanism to check your answers or your analysis, because you cannot really proceed to your shear and moment diagram if there's a problem with your load diagram. So I think we are now ready to proceed to the shear diagram using our load diagram here. Okay, so using our load diagram, okay, first for the column, okay, we have this as our column AB. Okay, so start with from lower up to the upper. Of course, 5.85 has nothing, has no shear effect. Of course, this 1.46 has. So it will push inwards for the shear. So that is the inward push, and it will maintain the same value until B. So until B, it will go back to 0 because of this leftward force here. So here it is. And it had remained to 1.46 until it yielded to 0. So we are done with the column. So for the inclined member, we have this as our inclined member, and then we refer to the components we have just resolved a while ago. So of course, we do not need to go over with these actual forces here. Our concern is just the y prime, okay, because it has the effect on the shear of this inclined beam. So first, we will have an upward 4.14 that is to be deducted by 1.032, and that will yield to a positive value 3.108. And then we deduct, of course, the mother force equivalent to 0.293, okay, 0.293 times 14.14, we have equal to 4.14. So from 3.108, we deduct 4.14. So we have negative 1.032 on this point. And then it will eventually close to 0. Okay, so we're going to connect this by a straight line and look for this distance. Say that is, if this is x, this is 14.14 minus x. So we use the ratio and proportion by similar triangles. We have x is to 3.108 as to 14.14 less x is to 1.032. So therefore, x now shall be equal to 10.62 feet, and 14 minus x is equal to 3.52. By the way, this is 14.14. Okay, so what for that we are getting this dimension? Of course, we need to compute for the area of this before we proceed to the moment diagram. So let us compute for the areas. So first, for this rectangle, we have 14.6. We have 1.46 times 10 is 14.6 square foot. Okay, so next, we have here 3.108 times x 10.62 divided by 2, or triangle area. We have here 16.5, and that is 1.82. So finally, for the moment diagram, of course, we need also to note our moment at B here. Okay, so if we have the column, say this is the column AB, and of course from this up to this point we have 14.6 value here, and that is inwards, so that is negative. So the connector is straight line. Okay, so because of the moment at B, that is equivalent to positive 14.6, to just close to 0. So it will close to 0. And then for this inclined member, we also start with your moment here. So what is your moment a while ago? We have negative 14.6, and then we add here the positive 16.5, so it will lead back to positive value here, and this is equivalent to 1.9 here, and then we deduct here the negative area 1.82, so it will almost yield to 0. So this happened because we have the rounding, so the effect of rounding off causes this to have an error on the rounding off. Okay, so but 1.91 minus 1.82, it will be yielding to closest to 0. So there will be no problem with that. Okay, this is also acceptable to have a value so close to 0. So sometimes you cannot perfect this because of the rounding off. Okay, so we need to connect this dotted line here by uh, parabolic curve, since this is a first degree curve that is decreasing. So obviously this will be connected by a concave downwards curve. So here it is. So this will now be our shear and moment diagram for this frame. So as a summary, the key to the frame problems, especially in an inclined member, we'll just have to make a way to resolve all of your forces along the parallel and the perpendicular axis of this inclined member. So the most basic or the most significant skills we wanted to have here is by component, or getting the component by mastering the transfer of the angles and then the trigonometric functions. Okay, so this is for the problem for today, and see you on the next video on complex frames, getting the shear and moment diagram. Okay.